today discussing some important signals, and those signals are particularly important to us because they happen in many physical systems. They exist in many of the other subjects of computer engineering or electrical engineering that you study. And they serve also in some cases as identifiers for systems. We will see that later when we come across it in the next few lectures. The first among these important or important signals or type of signal is the complex exponential signal. So what's the complex exponential? It's a signal that has, first of all, it's exponential, which means that the time variable, the independent variable, is in the exponent. This is where we have the independent variable. So it is in the exponent of the e function, the exponential function, okay? Not only that, but that time variable is multiplied generally by a constant which takes a complex form in general. So this S can have a real part and an imaginary part. In addition to that, there is an amplitude, a constant amplitude, so it's not time varying, a constant amplitude, which also, generally speaking, belongs to the set of complex numbers. So C here is a complex number. Also S is a complex number. C and S both belongs to the complex number. The special case of that is when C and S both belongs to real number. That's the typical real valued exponential function that can be either decaying or growing, right? That's the one that you have learned a lot before. While here we are more concerned about the fact that this S can take a complex value, which means that it can have an imaginary part as well as a real part to it, okay? This is what differentiates those complex exponential signals from the real valued typical exponential signals as a function of time that we have studied before. So remember, for the real valued one, it was very simple. If you want to remember, so this is how e to the, so this is e to the at, right? And this was e to the minus at. This is the real valued signal, right? Both of them, they pass through 1. So this point should be intersecting the y-axis at 1, right? So these are the typical real valued exponentials. Now, when we talk about complex exponentials, the signal does not look like this. It looks completely different, and we will go through that step by step, okay? First part is we consider the situation where C takes a general form. So C is a complex number, and it can be written in its polar form. Remember, the polar representation of complex number is a magnitude multiplied by e to the j phi. If you haven't studied that before, I will give you a primer quickly on a complex number or a refresher or a reminder or whatever you like to call it. Okay, so C in general is a complex number, and it can be written either in its Cartesian form, so some real plus j multiplied by an imaginary value, or it can be written in the polar form, a magnitude and a phase, right? Okay. So here we write it as a magnitude and a phase because that makes it easier to incorporate it into the expression that we see up there. So C, when it's written as A, where A is a real number, e to the j phi, where phi also is a real number, right? Then when it's multiplied by e to the power st, you multiply the amplitude outside the exponential, you keep it. So the A stays before the exponential, and then whatever phase term here, you add it to the exponential exponent, right? That's why we write it in the polar form, okay? Now, C takes a general form, while we assume here that S, in this slide, we will take the general form in the next slide, is pure imaginary only. So now we are considering an initial case where S is only pure imaginary, so it doesn't have a real part, only has an imaginary part, j omega naught, okay? So S is equal to j omega naught, while A can take any general complex form, and we write that form in the phasor or polar expression. In that case, your signal, x of t, so this was your original x of t in the general form. Now, if we replace C by this expression, and we replace S by this expression, we end up with this final expression for X, right? Anyone has a problem figuring out where this came from, starting from that, given that S is equal to J omega naught and C is equal to A to the J phi? Anyone has a problem figuring out where this came from? If you have, ask. There is no shame in asking. Not clear. Zoom. Like this. Okay. Is it clearer now? Okay. I don't know how to make this actually bigger. It's not using the full screen. I'll try to figure this out, but probably not in today's lecture. Okay. So, is it clear to everyone where this came from? Just substitute in that expression C equals A to the J phi, where J is the root of -1, phi is real and A is real, and substitute S equals J omega naught, where omega naught is a real number and J is the root of -1. Yes?
Why we did this? Like, why we change the C to this form?
We didn't change it, we expanded it. So we say that generally speaking, C is a complex number. We want to incorporate that into the expression of the exponential without having to say again, I have in the magnitude a real part and an imaginary part. So now we take the effect of C in terms of a phase and amplitude. So the phase will be added to the exponent, right? And the magnitude will be just multiplied by the segment. So we end up with an expression that has a real magnitude and some real phase term, right?
There is no imaginary.
No, the imaginary is up there.
The J.
Yeah. So it's still a complex number, but we will see what does it mean. Okay? So we ended up with x of t given as some magnitude and some phase, which is a pure imaginary complex exponential, right? The phase comes from the S, J omega naught, and the e to the J phi will multiply by e to the J omega naught t, right? It produces another phase, so it's just e to the x multiplied by e to the y is e to the x plus y, right? So this is what we ended up with. Okay? Now this expression.
His question.
Yes.
And S is always represented by the imaginary.
Sorry.
S
S.
Is always represented by the imaginary.
No, we said only here we assume that S is pure imaginary. Later,
Only in
the
this
next
case.
slide, we will see the general case where S has a real part and an imaginary part.
Okay.
Now we are just considering the case S is pure imaginary. Okay? And we will look at it, get some understanding, and then we move to the more general case where S
Is
has a real part and an imaginary part. Okay? That's the next slide. Okay? So now this final expression, regardless of the values here, is some magnitude and then a complex exponential. That complex exponential has only a pure imaginary part, which is called phase, and that phase is a function of time, right? Okay. Now, what do you know from, that's where I need to discuss with you a little bit complex number, like a primer on complex number. So remember, complex numbers right, are generally written, if I have a complex number x, then it's written as some real part plus j or I multiplied by some imaginary part, right? Where both I and r, they both belong to the set of real numbers, right? So x belongs to the set of complex numbers, but the two components of x, the real part and the imaginary part, are just real numbers, okay? And then we called this representation the Cartesian form, right? Cartesian form. Okay? This form is very useful when you are trying to add or subtract complex numbers from each other. So if I have x1, which is r1 plus j i1, and I have x2, which is r2 plus j I2, and I want to add x1 plus x2 or subtract, then the result is simply R1 plus R2. That's the real part, plus J multiplied by I1 plus I2. So I add the reals together and I add the imaginaries together, right? So we use this Cartesian form when we are trying to do additions and subtractions, okay? There's another form where we represent x as some amplitude and some phase term, right? E to the j phi, where phi again is a real number and a is a real number. This is called the polar form. Okay, and this as well, they belong to real numbers, the set of real numbers. Okay. Now this representation as a magnitude term or amplitude term and phase term is useful when we are trying to do multiplications or divisions. So if I have x1 and x2, so x1 is equal to a1 e to the j phi 1, and I have x2 which is equal to a2 e to the j phi 2, and I want to multiply them, so x1 times x2, simply it's a1 times a2, the magnitudes are multiplied together, and then e to the j, and you have phi 1 plus phi 2. I run out of space. The phasors are added together, right? Or the phases are added together. So that I will show you. Right? And if you do divisions, you divide the magnitudes and you subtract the phases, right? So it's much easier to deal with the polar form when you are doing multiplication or division of complex numbers. Now, how do these two things relate to each other? Remember that when we want to represent complex numbers, we represent them in the complex plane, where the x-axis is the real part and the y-axis is the imaginary part. And if I have this, let's say R1, I1, then if I want to represent this one, x1 for example, then I move R1 in this direction, and then I move I1 in that direction, and this becomes my point x1, right? Similarly, I can express this x1 by two other quantities, which are the angle here, right? This is phi 1, and the length, which is a1. So these are two ways to eventually reach the same point x1, either by x and y or distance and angle, right? So that angle and distance is what we call the polar form, and that x and y is what we call the Cartesian form. It's the same thing to determine the same point, okay? How do these values relate to each other? Remember? So the R, or the amplitude, is equal to the root of real squared plus imaginary squared, right? And the phase, phi, is equal to tan minus 1, the imaginary divided by the real part, right? So this is how you get the amplitude, the distance here, and the angle here from the real part and the imaginary part. If you want to do the opposite, if you have A1 and phi 1, and you want to get R1 and I1, then R1 is equal to A1 cosine phi 1, and I, the imaginary, is equal to A1 sine phi 1, right? So this is how you get Cartesian from polar. This is how you get polar from Cartesian. If you know one representation, you can immediately figure out the other, right? I think this is like basics of complex numbers. I hope you have been through this before at least once, either in high school or here in the university, okay? Now, what does complex numbers represent? They simply represent two-dimensional numbers, right? These are actually, in real life, if we represent some physical quantity with complex numbers, we are actually dealing with two real numbers combined in one representation. So something with two dimensions, okay? If you are, for example, talking about communication systems, then you are and those two components are orthogonal to each other. So you are sending some of your information on a sine carrier and the other information on a cosine carrier. And then if you learned a little bit either later on in the signals and systems, or if you had some exposure to communication, when you receive something on a cosine carrier and you try to bring it down or read it using a sine, it will not read anything. It will only be read if you use a cosine again. And similarly, when you receive some information put on a cosine signal and you try to read it with a sine signal, it will never be read. You have to read it using a cosine signal. We will come to that later.
We inverse it?
It's not inversing, it's inversing the operation, but the inversion is done by something called correlation between functions. We'll come to that a bit in the advanced part of the course as we move forward, okay? But the important thing is just to visualize what complex numbers mean. They are simply two-dimensional real numbers. So real numbers that has two components instead of one component, okay? That's what complex, but they become very convenient when you are trying to do operations on those two-dimensional real numbers. When you want to add them, multiply them, divide them, do some processing over those numbers in a unified way, the complex representation makes this much more convenient mathematically, okay? Important thing is to know that this representation is simply what? Now imagine that our signal is no longer with constants, right? Imagine that I just want to write this A1 e to the j. Now let's make this a function of time. So omega naught t let's remove the one, just keep it as a, okay, e to the j omega naught t plus some phi. Oh, it became much thicker. Okay. Now this, as we said, can be broken into the Cartesian representation. What's the Cartesian representation? The real part is a cosine, the phase here, right? The whole phasor term. So that's cosine omega naught t plus phi, right? And then this is the real part. All of this is r. And then plus the imaginary part, which is j multiplied by sine omega naught t plus phi as well. All of this is my imaginary part, right? Now notice that a with a complex exponential, which is a function of time, ended up being a cosine function and a sine function, but in two dimensions. One in the imaginary dimension, one in the real dimension, right? A cosine is a periodic function, right? We studied earlier, you know from many mathematical courses that you have been through, that cosine is periodic. And the period of this cosine is what? If omega naught is the angular frequency, what's the period of this?
Like for one period or?
Yeah, what's the duration of the period? How do you calculate the period of this? It's a function of omega naught. How does it look like?
Is it 2 pi s or 2 pi over t?
Yeah, so 2 pi over omega naught, right? 2 pi over omega naught. That's the period of that one, right? Because if it was just the Hertzian frequency, not the angular frequency, so if it was f, right, then the period is 1 over f. To get 1 over f from 2 pi f, you need to multiply by 2 pi, right? So 1 over 2 pi f is 1 over omega naught, and you multiply by 2 pi gives you 1 over f, which is the period, right? So t, the period of each one of those, is equal to 2 pi over omega naught, okay? This is the period of the sine and the period of the cosine. Now if I have two-dimensional signal, right, and in both dimensions it has the same period, what's going to be the overall period of this? Same, right? Because again, if I somehow move along the x dimension and the y dimension, a duration of 2 pi over omega naught, the signal is going to repeat. Both the real part and the imaginary part are going to repeat, right? I move another 2 pi over omega naught, both the real part and the imaginary part are going to repeat again, right? Which means that the overall e to the a j omega naught t phi is going to repeat every 2 pi over omega naught, right? So this means that the complex exponential function is simply a periodic function. A function with period equal to 2 pi over omega naught. Keep in mind, we are still talking about the situation where S was only j omega naught, right? We did not discuss the case where S has a real part and an imaginary part. This is the simpler case, and we know from that case, going back to our slide, that this function, right, is a periodic function, and the period of that is equal to 2 pi over omega naught. It's just two-dimensional, but it is still periodic, right? It has 2 dimensions, real and imaginary, but it is periodic, and the period of that is 2 pi over omega naught. Don't forget something, that when we discussed periodic functions, we also touched upon the reality that any function which is periodic with period t is also periodic with 2t, 3t, 4t, 5t, and so on, right? But what we care about is the fundamental period, the smallest duration after which the function repeats again. Okay? So here, the fundamental period, t naught, is equal to 2 pi over omega naught. But it is still periodic with 4 pi over omega naught, 6 pi over omega naught, 8 pi, 10 pi, whatever. Multiples of that are still periods of e to the j omega naught, but they are not the fundamental period. So when we say periodic with period, whatever number, we are talking about the fundamental period. Okay? Any questions so far about the complex exponential? So the idea here was to give you 2 important ideas, right? Or 2 important concepts. The complex exponential is simply a cosine and sine orthogonal to each other, one in the real direction and the other component is in the imaginary direction, right? And because the cosine and sine have the same period, then we know that this complex exponential function is a periodic function. So number 1, it's sinusoid with 2 components, right? Cosine and sine, we call both of them sinusoidal functions, right? So it is sinusoidal function, and it has a period equal to 2 pi over omega naught, okay? That's the 2 important concepts that we wanted to understand about the concept, the complex exponential. Why do we care about the complex exponential? Because it allows us to represent signals as we come later, in the frequency domain, which means we represent the variation of a signal versus frequency instead of representing the variation versus time. We will come to that in a few lectures, the frequency domain representation. Yes, and it allows a generalized representation in frequency domain. Yes?
When you read on the yellow ink, how did you get J sine omega?
Which part?
Sine. How do you get J sine?
Okay. We agreed that this expression is a polar expression, right? And if you want to map it into Cartesian, real plus j imaginary, what do? You need to calculate the r, the real part, and the imaginary part. And we wrote the equations that allows you to calculate those from the polar part, right? The real is equal to a cosine the angle, right? The amplitude multiplied by cosine the angle, and the imaginary part is equal to the amplitude multiplied by sine the angle. Where is the angle in this case? It's this whole expression, right? And where is the amplitude? It's this, right? So if I want to break this complex exponential into its Cartesian components, the real and the imaginary, then it's the magnitude multiplied by cosine this thing, that's the real part, and the magnitude multiplied by sine this thing, which is the imaginary part. It is A. I missed the A. If that's what you're asking about, it's just the A missing is here. Yeah. Okay. Yes, it has A, definitely. Okay. Any other questions? Okay, now the next part is going to discuss, okay, we agreed, the first part of this slide, okay? We agreed that the complex exponential is a periodic function and it has a fundamental period 2 pi over omega naught, and it has a fundamental frequency omega naught, right? That's the smallest frequency. Now, generally speaking, from a cosine function, if you go and multiply the frequency by 2, right, then you get a faster one, right? Still periodic, but the period now becomes half the previous period, right? So you grow the frequency and you shrink the period. The multiple integers of the frequency of a cosine function are called, typically they call them in the engineering domain, they call them the harmonics. So if you have cosine omega naught t, that's the fundamental harmonic or the fundamental frequency or the first harmonic. And then cosine 2 omega naught t is called the second harmonic of cosine omega naught t. It's the one with double the frequency, right? Cosine 3 omega naught t is called the third harmonic, the one with triple the frequency, okay? And so on. Okay? So these are called the harmonics. Why do we care about those harmonics of a fundamental complex exponential signal? Because later on, when we discuss in the next chapter, when we discuss the frequency domain representation of periodic signal, if you have a general periodic signal which is not sinusoid, for example, a signal that looks like this. So you have something like this. And it repeats everywhere, so it continues the same way. This is periodic, but it's not sinusoidal, right? Now we can break this signal into a summation of sinusoidal signals, right? And those sinusoidal signals are going to be with, first of all, this is periodic, right? So if it is periodic, it has a fundamental period. And that period, if you reverse it, you get a fundamental frequency for this signal, right? And then if you take that fundamental frequency, it will be the main component of the cosines that represent this signal, right? But it will also include double that frequency, triple that frequency, 4 times, 5 times, and we call those the harmonics of the signal. Why does it contain more than one sinusoidal frequency? Because it's not as smooth as the sinusoidal function, right? So the sinusoidal function includes a single frequency. This one, which is not smooth, like squares here or triangles or whatever, it does include the main sinusoidal, which is smooth, and added to it another faster sinusoidal, and then added to it another faster sinusoidal, and so on, with different amplitudes and phase shifts. And when you add all of those together, you can get up to infinity, so there are many of them. You can get the original square function, which is periodic, right? We call that the Fourier series analysis. We will come to it. The most important part right now is, because of that Fourier series analysis, we do care not only about the complex exponential function, but its harmonics as well. It's multiple frequency or frequency multiples of the base complex exponential function. Okay?
Doctor,
Yes.
the 1, 2, 3, 4, what does it represent?
Multiples of the frequency. So the first harmonic, second harmonic, and so on. So I have a fundamental frequency, and then double the frequency, triple the frequency, 4 times the frequency, 5 times, and so on.
Like each period, it's one increase, one increase.
Not periodic. For each k, we get another sinusoidal or another periodic complex exponential, which has multiple frequency of the original fundamental one. So we have e to the j omega naught t. That's one sinusoidal or complex exponential with frequency omega naught. And then when we put k equals 2, we get 2 omega naught t, e to the j 2 omega naught. That's another complex exponential with double the frequency, and so on. So every time we set a value for k, we get a complex exponential with multiple frequencies of the original one. Okay? We call those the harmonics, just naming convention. So when you talk about harmonics later on, you know what do we mean by harmonics, okay? Now, the other important thing is, let's look at the situation where S is no longer pure imaginary, but it has also a real component to it, okay? And let's look at what happens in our expression. So when we take S with this general form, sigma plus j omega naught, so a real part plus an imaginary part, right? And then we expand the previous expression that we had. We end up with A, the magnitude, e to the j omega naught t plus phi, the part that includes periodic complex exponential signal, and then we have also e to the sigma t. Right? So as time goes on, what happens to this part? It either grows if sigma is greater than 0, or this will attenuate if sigma is smaller than 0, a negative number. Which means what? If we agree that the e to the j omega naught t plus phi in general, regardless of the amplitude, so let's say amplitude A, is in real and imaginary part a sinusoidal function. So let's say we take the real part, which is the cosine, so it will look like this, right? With fixed amplitude A, right? Now, if we say that as time, so this is how time moves. As time moves, we have also this term multiplied. So e to the sigma t is multiplied by this, which means if sigma is greater than 1 than 0, then we'll have something that grows the amplitude as we go with time, right? So we will actually have this sinusoidal signal growing as we go with time, right? And to the opposite of that, if we have sigma, so this is sigma greater than 0. And if we have sigma less than 0, then we have some decay in the magnitude. And our sinusoidal signal is gonna become smaller and smaller as we move, right? So now for the case, for the general case where S is a full complex number, not just pure imaginary, but it has also a real part to it, we no longer have periodicity because the signal is not repeating, right? It grows, so it doesn't look the same as you move, right? It's no longer periodic. Not only that, but in the case sigma is greater than 0, it's a growing exponential, it's a growing sinusoid. And if sigma is smaller than 0, it's a decaying sinusoid. Why do we care about this case? This is very important when you study systems at the transient situation. They are just being exposed to the input. So the system was stable and nobody is touching it, let's say switched off, and then at some point you start switching the system on, right? Now in that case, the response of the system to the input is gonna take, and you studied that maybe in your circuits 1 or electronics, right? And it starts ramping up with the input. So it starts growing or responding to the input over time. And sometimes when you are switching off, then you have the ramping down. Sometimes when you are introducing disturbance, the system behaves in a very bad way, but that bad behavior, which is called transient, decays with time until it becomes stable and produces some useful output, right? So the study of systems requires, in many cases, that we look at a situation where we are not just dealing with a sinusoid that has existed since minus infinity and will keep on carrying until plus infinity. In some cases, we have to consider the initiation or the termination effect or the sudden change of the input. And in those cases, you have one of those like growing or decaying behaviors. Okay? So that's why we still care about that case. We will only care about that case when we go particularly to the Laplace transform representation of signals. I think you studied that in your math 4, calculus 4 or something, right? The Laplace transform. Didn't take calculus 4? Yes. You didn't take any courses in math or what? Anyways, okay. Last thing is, again, a reminder that since the complex exponential includes both the cosine component as the real part and the sine component as the imaginary part, then you can always write this equation. I can deduce the cosine component or the real part by simply taking the real of the complex exponential representation, and I can deduce the sine or the imaginary part by simply taking the imaginary component. This operation means go for this complex number and only pick the real part. And this means go for this complex number and only pick the imaginary part out of it. So that's just a mathematical notation. And again, the periods of each one of those, the cosine and the sine component, is the same, 2 pi over omega naught. Okay, last thing related to complex exponential. Remember we studied earlier that you can measure the size of a signal by either measuring its energy, some quantity, we call it the energy. It's not physically the actual energy. It's simply the integral of square the magnitude of the signal, right? And we mentioned that sometimes, particularly for periodic signals, if you try to measure the energy, you will find it equal to infinity. So it's not a good tool to compare periodic signals together, right? All of them will have infinite energy because you keep on, like periodic signals by definition, in the ideal theoretical representation, they have to exist always from minus infinity to infinity. They cannot just start at some point and finish. If they do that, they are no longer periodic, right? Because if you take a signal that starts at a certain time and finishes at a certain time, and before and after that it was equal to 0, and you try to shift it, it doesn't repeat, right? If you shift it right or left as per the definition of periodicity, it doesn't repeat. So for a signal to be really periodic, it has to exist from minus infinity to infinity, right? And since those periodic signals exist from minus infinity to infinity, the energy is always equal to infinity. Our option in that case is to calculate the power of that periodic signal and compare them based on their power. What's the power of a signal? It's the energy divided by the whole duration of the signal. Now it becomes very challenging to calculate that for periodic signals because you have to do that calculation over infinite duration, right? So the calculation includes some values that goes to infinity, even though they cancel mathematically. Now, how do you do that? We observe that, let's say that this is our periodic signal. So let's say it looks like this. It's not sinusoidal, it's triangular, okay? Now, if I want to calculate the power over one period, what do I do? Just the power contained in one period. I calculate the energy of that period, right? Which is the area under the square of the curve, okay? Like multiply the curve or square the value of the curve and then calculate the area under that. And then I divide it by the duration, t. Now, if I want to calculate the power contained in two periods together, what's gonna be? This area added to it this area, which is just double the value. And then I divide by the whole duration, which is t plus t. So you double the value of the energy and you double the duration. Now if you keep doing this until you go to infinity, the value is gonna stay the same, right? Because if you take 2 divide by 2, it cancels. 3 divide by 3, it cancels, right? So we see that for periodic signals, we can calculate the power by only calculating the overall power by only calculating the average power of one period only. And as we go to infinity, this will keep repeating, and the duration will keep repeating with the same scale. So you end up with the total average energy of that signal exactly equal to the average, power, exactly equal to the average power contained in one period only. So for periodic signals, to calculate the power, we only need to consider one period of the signal, and then calculate the energy under that period, divided by the duration of the period, you get the overall average power of the signal. Okay? Anyone has a question about this? So the same happens for those cosine functions or complex exponential or whatever. Okay? Any periodic signal, this is true for it. To calculate the power, you need to only consider one period and calculate the power over that one period, and it's the same for the whole signal. Okay يا بنات؟ اوكي. انا خايف تكونوا ما بتسالوش عشان تهتوا مني. ما بتسالوش عشان الامور واضحه ولا ما بتسالوش عشان تهتوا؟ نص نص، شويه كده وشويه كده. اوكي. يس اتفضل.
يعني نحن we will calculate one period عشان نجيب الباور صح؟
You calculate the energy in one period. المثلث ده مثلا is let's say it's x and then x minus 1 minus x. تمام؟ اللي هم اللاين اللي طالع واللاين. To get the energy you need to square that, so it becomes x squared and 1 minus x squared. 1 minus x all squared اللي هو هيبقى كأنه decay كده. Now to calculate the energy in that, you just integrate that over 1 period. اللي هي T.
عشان يجيب
Okay.
الباور.
Now you get the power in 1 period. This is exactly the same as if you have done this
For
for
all.
all different ones, because
So-
as you grow the energy, you grow the duration exactly with the same scale. And since they are divided
بس
on
يعني
each other.
يكون في limit like points صح؟
Yeah, points are your start of the period and the end of the period. Start and the end of one period. Yeah. No, no.
يكون infinite.
If we want to calculate over one period, then we start our time at the start of that period and we finish at the end of that period. تمام؟ Okay. Any other questions? طيب. Unit step now, we are moving to another important function, which is called the unit step function. The unit step function is graphically represented as you see it here. So it's equal to 0 everywhere in the negative side, and it's equal to a constant with value 1, starting from time 0 all the way up to infinity. So on the positive side, including 0, it's equal to 1. In the negative side, it's always equal to 0. We call that function the unit step function. Okay? Now, why this function is important? Because it allows us actually to represent functions that are initiated at a certain time. So rather than, for example, the e to the minus at as a function, it exists from minus infinity to infinity, right? And the graph for e to the minus at would look like this. If you draw just e to the minus at, it looks like this, right? And it starts from minus infinity and it goes all the way to infinity. So this is e to the minus at. Now, if I want to represent a situation where I have the exponential, the negative exponential, e to the minus, or the decaying exponential, e to the minus at, but I'm saying that it only started at time 0. Before that, there was no signal. So my signal starts at a particular time, and then it continues with me. The unit step function is very useful in doing this presentation mathematically, because the only other option is to write this as a case. So if I want to say how this curve looks like, I might say that x of t, right, is equal to 0 when t is smaller to 0, and it's e to the minus at when t is greater than or equal to 0. That's one way. This is called the case representation, right? Mathematically, dealing with the case representation is not very easy. If you want to do algebraic math between different functions, okay? The other option is to say that this can be written as the e to the minus at multiplied by the unit step function. Why this is the case? Look how the unit step function looks like. So this is how the unit step function looks like, right? It's fixed value here equal to 1 and 0 everywhere in the negative. This is your unit step function. And then that curve, the e to the minus at, is something that looks like this, right? So it comes from here and it goes all the way from minus infinity to infinity. When you multiply those together, when you multiply those graphs together, what happens? All the values here are multiplied by zeros, right? So whatever value here is multiplied by a 0. Whatever value here is multiplied by a 0. So you end up with the result in the negative side, it's always 0. The result of the multiplication, okay? And on the positive side, what happens? Any value here is multiplied just by a 1. So the value stays as it is, right? I take the value of this curve multiplied by the corresponding value here, which is 1. So it stays the same. Take this value multiplied by the corresponding, which is 1. Stays the same. So you end up in the positive side with, right, the positive part of the curve as is, right? So I was able to deduce this without using the case representation. By saying what? By saying that this curve can be written as a general function as e to the minus at multiplied by the unit step. And the result is going to be this curve that I see here. Clear? So this is why we use the unit step function. It's a very useful function mathematically. Now a question for you. What if I want to do something like this? So I want something that rather than starting at 0, it starts actually at time 3, for example. What would this be?
U of t minus 3.
Exactly. Remember time shifting, right? If this is u of t, right? So it's 0 here, and it jumps up to 1 at 0, and I want to do something similar, but it's shifted to jump at 3, then this is simply u of t minus 3. What if I wanted to start in a negative part? So it becomes u of t, let's say plus 2, for example. Right? Minus 2 will start in the positive side at 2. Plus 2? Minus 2, sorry. Okay. Okay, a question. What if I want the unit step to exist in negative, not in positive?
Minus
The inverse?
Time inverse. Yeah, minus t. So this is u of minus t, right? So it has 1 in all the negative side, and it has 0 in the positive side, okay? And what if I wanted to start at time 3 and goes in the negative direction? So if I want something that looks like this, starts here at time 3, but it goes this way, not the other way. So u of negative t right? Because we agreed that you have to look at the sign of the shift and the sign of the time. If they are opposite, then that's a shift to the right. If they are the same, that's a shift to the left, right? So this is u minus t shifted to the right, okay? Okay, nice? Okay, given all this, let's see if it's really nice. Tell me, and you have to work this together in a couple of minutes, just focus on the first one. Tell me, how can you get this function, which is a pulse that exists from 2 to 4, and it has a value equal to 1, without using case, only using unit steps. So tell me, how can you get this shape using unit step functions only? By adding unit steps, by multiplying, by dividing, by doing something, shifting, whatever, a combination of unit steps that allows you to present this function. Tell me how it looks like. يلا فكروا and try to do it, and then show me. تعرفوا على بعض أول مرة؟ تعرفوا على بعض أول مرة؟ هاي. Remind me to. يا بنات. خلاص 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 خلاص. At least I can think of two ways to do this. تمام؟ Okay, تمام? There are two ways to do this. Okay, the first way is by doing multiplication, and I can think of it this way. Like initially, how do I think about solving this problem? I want something that starts at 2 and gives me a value of 1. Apparently, this is unit step of t minus 2, right? So that's my first step. Okay, but the problem is it continues all the way. Now I want to bring it down. Right? I want after 4 to bring it back to 0. Either I multiply it by 0 starting from here ongoing, or I subtract from it 1 starting from here ongoing, right? So let's think about the two approaches. If I want to multiply it by 0, right, then I need to make sure that whatever I multiplied with will give me zeros here and will give me 1 here. And then I don't care what it gives here because it's going to be multiplied by 0 anyways, right? Okay, so what I can think of in that case is something that gives me zeros in this part so that it cancels this, right? And it doesn't cancel this, so it must be 1 here. And if I continue to make this a unit step, it becomes unit step of minus t plus 4, or 4 minus t. If I multiply those two together, the upper function and the lower function, right? then what I get is in this range 1 times 1, 1 times 1, 1 times 1, 1 times 1. So in this range, it's going to be, in this range, it's going to be 1, 1, 1, 1, 1. That's the value. And then once I reach this point ongoing, it's 1 times 0, 1 times 0, 1 times 0. So it's 0 here. And once I reach this point, it's 1 times 0, 1 times 0, 1 times 0. So it's also 0 here. So this is exactly the pulse that I was looking for. So that's one way by doing multiplication of 2 unit steps. In many cases, the representation with multiplication, in many cases, but not in all cases, makes the calculation harder when you start doing operations after that. So if I can find an addition and subtraction representation, it might be convenient. Let's try to see how can I find an addition subtraction representation. So if I take this, right, which is u of t minus 2 as a start point again. Now I want something to subtract it from that such that it cancels only this part, but it doesn't do anything here. And it doesn't touch this part as well. So it must be something that starts here and it's equal to 1, so that when I subtract it, it cancels this part. And it must be 0 everywhere else, so it does not affect anything before t equals 4. So this is a u of t minus 4. And then u of t minus 2 minus u of t minus 4. What happens? Here 0, 0, 0, 0, subtracted from it 0, 0, nothing happens. Once I reach this point, it's 1, 1, 1, subtracted from it 0, so it stays as 1. Once I reach this point, it's 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, which is 0 again. So now I can get the same pulse using subtraction of 2 unit steps. خلاص? Any questions? Yes.
I didn't get the second.
This is u of t minus 4. تمام? It starts at 4 and then it goes to infinity with a value equal to 1. تمام? This is u of t minus 2. It starts at 2 and goes to minus infinity with values equal to 1. If I subtract those two functions from each other, what happens? Subtract. أطرح دي من دي. u of t minus 2 minus u of t minus 4. تمام? Let's see. Here, the minus means take every value of u of this upper function, subtract from it the value of the lower function. Here, 0 is subtracted from each other, which is 0. Right? When I reach this point, this function is equal to 1, while this is still 0. So it's 1 minus 0, that's 1. 1 minus 0, 1. 1 minus 0, 1, 1, 1. So I still have 1 here. Right? Once I reach this point, the upper function is 1 minus the lower one, which is 1. 1 minus 1 is 0. 1 minus 1 is 0, so it goes back to 0 again. Okay? Clear? Yes?
So we can, we have two solutions.
We have what, sorry?
We have two solutions.
Yeah, for this case, you have two solutions. Both are correct. Right? So you can do this solution or that. Maybe you can come up actually with one more solution. There are more complicated ways to do this. Yes?
Isn't the second solution just
The window, yeah, yes. You mean the window function هنا, you mean pulse function أو window function. هي دي actually is a window function.
So we can just write the window function.
No, I said in terms of unit step. So you have to show me how you calculated that from the unit step. Don't just say the window function, right? Now, the other one is a bit more complicated. I don't want to do it here in class. It's solved actually in your book. You can look it up. The idea here is you cannot just simply use unit steps only. You still have to consider the equation for this line and the equation for this line, because it's not just simply constant value, right? It's a sloped line. It might be a curve. It might be anything else. In that case, it's not only unit steps, but unit steps multiplied by some functions, right? Which are the functions that represents this straight line and this straight line and so on. It's solved in your book, so try to do it by your hand and look up the example in the book as well. It's an example in the book. Okay? طيب. I think we'll finish in 3-4 minutes. The last, but the most important function that we will consider today is something called the impulse function. I don't know, probably many of you have not heard about that before. Probably you heard about it in math, so it depends. Okay, The impulse function, and sometimes it's called the unit impulse function, sometimes it's called the Dirac delta function because it's typically represented by the Greek letter delta, okay? And it was discovered, we call it the Dirac because it was discovered by a mathematician with the last name Dirac, okay? Is a function that's defined in a very weird way. First of all, you cannot plot that function. I mean, it doesn't have a particular curve shape, okay? But we still can represent it on graphs with some symbolic representation. The function itself is defined as follows. The delta function is equal to 0 everywhere in time except at t equals 0, right? So what's its value at t equals 0? We don't know. It's a very large value, right? But the condition is the total area under the curve of that function, which is a very narrow curve, is equal to 1. So the integral across the function, which is 0 here and 0 here, and only has value around 0, right? Around time 0, that integral is equal to 1. So the overall area under whatever curve this function have, which we don't know how it looks like, the total area under that curve is equal to 1. Okay? That's why we call it the unit impulse function. Okay? You can imagine, one way to imagine this function, one way, there are many other ways, is a rectangle, okay, with a width equal to epsilon, so for example symmetric around 0, and it starts from minus epsilon over 2, where epsilon is just a small number, whatever, a real small number, okay? So it starts from minus epsilon over 2, and it finishes at epsilon over 2, so the width here is epsilon, right? And it has a height equal to 1 over epsilon. What's the area of this rectangle? 1. Because 1 over epsilon multiplied by epsilon, that's the area of the rectangle, it's equal to 1, right? Now, to make this a delta function, take the limit as epsilon becomes almost 0. Take the limit as epsilon goes to 0. What happens? Becomes narrower, 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 right? Almost around 0 only, but it becomes taller, because as this gets smaller, it becomes 1 over epsilon becomes a larger number, right? So it's very narrow, very tall. The only condition is it has to maintain an area equal to 1. Tamam? Why am I saying you cannot really say that this is a graph representation of this signal? Because someone else might come and say, no, 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 I'm not going to do it this way. I'm going to have a triangle, right, with a total area equal to 1. So the width over there is going to be 2 epsilon, and the height of the triangle is going to be 1 over epsilon. What's the area of the triangle? Half the base multiplied by the height. So it becomes again 1. And then I take the limit, so the triangle becomes narrower, and the pointy part goes up, 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 such that the total. So now someone imagined it as a rectangle, another person imagined it as a triangle. Actually, people, if they want to complicate things, they'll say, no, 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 no. I'm going to imagine this as a decaying exponential that starts here, right, and goes, so starts here at 1 over epsilon, and then it decays up to infinity, right? And then I increase the exponent value, so it becomes higher, and it decays faster, right? Until, so if it was originally like this, as I increase the exponent, it will come like this, and then like this, and then until it becomes with very large height and very small width, and still the total area is equal to 1. So you can imagine many curves, right? So there is no specific shape for the delta function. Only is 2 properties. Number 1, it's 0 everywhere except at 0. Number 2, the total area under that function is equal to 1. That's it. Any function that satisfies those 2 conditions is a Dirac delta function. Okay? Now, the question is, how is this useful? And the usefulness of this function comes actually from its mathematical properties, which is shown in the next slide, this one. So there are 3 important properties of this function. Okay? The first 2 are quite useful in terms of using it with other signals, and the third one is about an extra mathematical property of that function. The first one says that if I have a general function, phi of t, Let's say, for example, phi of t is this function. Okay, looks like this. This is phi of t, any general function. It has any shape, has any expression. Okay, and I multiply this with a delta function. Okay, and let me just go with the delta here. Okay, what's gonna be the result?
The value of it will be delta of
It will stay as a delta. That's the first important part, and it will have an area equal to the value of that function at 0, right? Again, why am I saying this? Remember, the delta function is 0 everywhere, right? And at 0, it has something. We don't know what. We call that delta, right? And the other function has values everywhere. So all these values are multiplied by 0 everywhere, except when they are at 0. When you take phi at 0. Okay? That value of phi at 0 is multiplied by what? By the delta. I don't know the value. I know that it is the delta function, because it always exists only around 0, right? So that phi of 0 is multiplied by the delta. So when I multiply a delta function by any general function, I get a delta again, but it is scaled by the value of that function at the location of the delta. Okay? I know we exceeded time, so I'll stop here. I will move to this.